Okay, welcome everybody. Welcome to the Controller Hardware in the Loop presentation hosted by the IEEE Region 4 and Typhoon HIL. We're going to kick off with some announcements by Jim Reese. He's our Industry Engagement Committee Chair. Jim has 53 years of IEEE service and has donated many hours to the IEEE. So over to you, Jim.
Okay. Thank you very much. Set here. Okay, I just want to tell the group here a little bit about the Industry Engagement Committee. And this event, the Controller Hardware in the Loop for Power, Electronic, and Controls Testing, presented by Matt Baker from Typhoon HIL, was organized by Dave Hoffman, project manager for the IEEE Region 4 Industry Engagement Committee. The IEEE Region 4 Industry Engagement Committee facilitates IEEE industry engagement activities broadly across Region 4, coordinates, identifies, and acts on opportunities, gaps, and overlaps across Region 4, launches initiatives, and recommends to the IEEE Region 4 Executive Committee needed development of products and services that meet the needs of industry, government, and industry officials. So the committee gathers input from the IEEE OUs, industry leaders, and professionals that will help in the development of its strategic directions related to the needs of industry, government, and industry professionals. The committee assists IEEE Region 4 with its industry outreach activities and by identifying other events and opportunities for focused interaction, supporting engagement and relationship building with industry, government, and industry leaders. Committee also monitors industry-related activities across IEEE Region 4, identifying opportunities to provide support, coordinating efforts where needed, leveraging successful activities, emerging efforts, and launching activities with the goal of strengthening and harmonizing IEEE Region 4 efforts aimed at addressing the needs of industry, government, and industry professionals. And it helps all IEEE organizational units, including sections and chapters, to form their own industry engagement committees. If you have an interest in working with or even providing input to this committee, please contact myself, Jim Reese, committee chair, at j.riess@ieee.org. And you will have seen that on your invite. You should have on the invite and the announcement, you should have that address. And I guess on behalf of Region 4, we thank you for attending. Back to you, David.
28 Jim. So I'd like to introduce Matt Baker, our presenter today. Matt has 28 years in the Marine Corps and retired as a colonel. Since retiring, he's been active in business development in the energy field. I'd also like to say for attendees, please use the chat feature if you have any questions rather than the Q&A feature. So the chat window is on the top right of your screen most likely, and you can minimize the Q&A. So with that, I'd like to introduce Matt, and full disclosure here, Matt is actually my uncle. So over to you, Matt.
Thanks, Dave. Can you guys hear me? Got a positive thumbs up. As Dave said, my name is Matt Baker. My title at Typhoon is Director of Microgrids and Critical Power. And just got a few slides to go through with you here today. Kind of start with the story of how a Marine Corps infantry officer ended up in power electronics and control modeling and simulation. Certainly doesn't have anything to do with infantry, and it doesn't have anything to do with aerospace engineering. I got those degrees way back in the 80s, and I don't think I can qualify as an engineer anymore. It's been a long time since I've used that. But when I retired in 2015, I got out, and I'm talking to you from Norfolk, Virginia, and my family said, you can move, but we're not going to move anymore. So I kind of had to figure out what I was going to do. And I ended up working for a small company called Earl Energy that was doing hybrid energy projects. And what I mean by hybrid energy, they were taking diesel gen sets and marrying a lithium ion battery to them, a little bit of solar PV, and making that diesel gen set much, much more efficient. And this company had a number of military projects, and I was hired because they figured, well, you can speak Marine Corps, so you'll be able to help us sell these things. Well, as it turned out, it's a lot harder to pull off the integration of power electronics and digital controls than people give it credit for. And our projects were over budget and late, and they were really giving us fits. And so I slewed from a business development role into a project management one. And we were clearly, our biggest issue was power conversion. We were using silicon carbide, wide band gap, kind of cutting edge at the time, power converters. And we couldn't get the controls right. The machine would shut down from time to time. So we hired this power electronics engineer, and the first thing he said was, where's our hill? Where's our hill? Got to have a hill. And I was excited. After 28 years in the Marine Corps, I finally felt like I was going to be able to contribute. And I said, I know how to take hills. By the way, why is that one spelled with one L? And he kind of slowed it down for me and explained what hardware in the loop was. Then I went and talked to all the other engineers. And to a man, they said, we don't think you need that thing. One guy, our embedded software developer, went out of his way to tell me that I can do everything that thing can do, the hill can do, on an Excel spreadsheet. And I said, well, duly noted, but this guy's really persuasive, and we clearly need something. So we purchased HIL, and at the time that was Typhoon 603. This was back in 2017. I knew it was a game changer for us because I walked into the company break room about 2 months later, and I saw a sign-up sheet with all the hours of the day and everybody's name dutifully listed. And I said, hey, what's this? Is this like the bake sale to save the company, or what's going on? And they said, oh, no, that's the sign-up sheet for the HIL. And I said, hey, Mr. Excel spreadsheet, I see your name all over this list. You know, what gives? And his only explanation was, well, life is tough. It's tougher if you're stupid. Hardware in the loop, and that's what I'm going to talk to you about today, was a game changer for Earl Energy. Helped us get all of our projects done, and we were very proud of what we delivered. It was too late in the sense to save that company, although the company is still a going concern, is FlexGen, with a completely commercial focus. But I learned a lot from it and introduced myself to the guys at Typhoon because of it. And that is the reason why, an infantry officer, aerospace, one each, ended up at Typhoon Hill. So a little bit about Typhoon. Founded in 2008. It's an MIT spinoff. The two brothers you see in the bottom right, Nikola Solanovic and Ivan Solanovic, both from Serbia.
Hey, Matt, let me jump in and interrupt. I don't think we can see your now.
Did we lose it somehow? Here we go. Let me try again. How about now?
Perfect.
All right. So, a little bit about Typhoon again. These two brothers in the lower right, both came to the U.S. to take their doctorates. One at Virginia Tech, one at MIT, and they had this notion to stand up this company to do hardware in the loop testing. We're quite proud of the fact that Ray Stata from Analog Devices, also a very famous MIT grad, and JJ Janopoulos, current professor at MIT, are also on the board. The company was founded in 2008. We have a very comparatively small office in the US, roughly 14 people, and then wholly owned subsidiaries in Switzerland, Serbia, Canada, and offices in Brazil, for a total of about 100 folks. We emphasize that we have U.S. person, engineers, and staff. That's particularly important today, as is this cyber compliance and government experience. But by no means are we a government-centric house. The original problem set that got Typhoon started was medium voltage DC drives. And from time to time, these very, very large scale drives would blow up and cause a great deal of not only safety issues, but delays to the project and whatnot. And they decided, hey, why can't we use hardware in the loop, which the aviation and automobile industries have been using for years? Why can't we use that in the power electronics space? And the issue was fidelity. And so these guys from Typhoon, our founders, invented this way using FPGA-based computing devices to really get after the fidelity. So we can do real-time simulations using sub-microsecond sample rates. And so that's what we mean by fidelity. Now, why has this become more important? And essentially has to do with microgrids. So everything's a microgrid, really, when you stop to think about it. I mean, there's a definition, distributed energy resources under digital control that can be either islanded or unislanded, is what the definition of them is. But when you think about it, that basically covers what we typically think of as a modern distribution center or distribution system, a ship, oil platform, electric mobility vehicles. All of these things are microgrids. And the problem is that these things typically don't play well together. Here's an example right here from Norfolk, Virginia, USS Ford, $12 billion. I think they're saying it's $13 billion now to build it. About $4 billion spent on commissioning it. It is really hard to get these power electronics, electromagnetic catapults, advanced ammunition elevators, radars, to play nicely together. People would love it if it was like a Lego block approach and they could just build their nice microgrid. The reality of the beast is it looks more like one of these crazy systems with roller coaster mentality. And the reason for that has to do with two aspects of a microgrid. The first of these is that they're very fast, and I alluded to that. And when I say fast, I mean in terms of the switching frequency of the power electronics and the requirements of those switching frequencies. And so you see in my diagram here, and by the way, I'll make this slideshow available in PDF form after the brief. Across the bottom, time steps, 10 nanoseconds, 100 nanoseconds, 1 microsecond, 10 microseconds, etc. That's extremely, extremely fast. And for the controls and power electronics, we say that you really have to be able to get into this 1 microsecond space, and Typhoon's starting to close in on the 100 nanosecond space in order to effectively model those systems. And you have a control layer, which is your actual digital or computerized control, and then the power electronics themselves. And you see here on my graph that we talk about a physical layer with computational complexity, that's the power electronics, and then the cyber layer, which is the digital controls. So before I get into that, just remember, microgrids are extremely fast. That inverter that is going to island for that microgrid, or that's controlling something on an automobile or energy storage, anything like that, it switches very, very fast. And in order to set up a simulation of it, you have to have an equally fast sample rate. The second thing about microgrids is that they're software controlled. And that seems kind of simplistic in the sense that, computers control everything these days. Well, the reason why that becomes very, very important in a complex system like a microgrid or ship or something like that is all of those different controllers for all of those different power electronic components. And keep in mind that even a relay, even a dumb on-off switch is now a computer controlled device with PMU measurements, et cetera, et cetera. That inverter is computer controlled. The gen set is computer controlled. Everything is controlled by a computer. And that means that there's lines of code associated with it. And you see this chart talking about the growth in lines of code between 2015 and 2020. And the takeaway here is how you effectively test all those lines of code. So if you've got a system and you switch say the inverter controller out, or you switch the battery management system, what is the effect of that switch of the controller or just a firmware update on that on the system as a whole, and how do you effectively test that? And it really is an overwhelming problem. A lot of software guys who are familiar with this refer back to this Toyota issue where there was this, problem with their accelerator pedal. And the biggest issue they had is they couldn't replicate it. They had people saying, hey, every once in a while I'm driving along and all of a sudden my car just starts accelerating. And the engineers used to say, oh no, it's due to the floor mat, it's due to whatever, because they couldn't replicate it. And really what it represented was just an explosion of lines of code that they just could not keep track of. So you have two kind of not so much related as very different, very unique, but extremely hard to address issues with modern microgrids. So with that, what we're going to talk about is how to have a model-based systems engineering approach to take that problem apart. So I'm building a slide here, and I'll just build it quickly to explain from Typhoon's perspective how we're coming after that problem. So you see, we're talking about a cyber physical model. And when Typhoon talks like this, what we're saying is the power electronics piece, the motors, the windmill, the PV, transmission lines, what have you, these are stable, predictable, reliable, not necessarily well known, but we can make a very, very accurate model of these. What we can't make an accurate model of, because they're constantly evolving, unpredictable, they're vulnerable to cyber attack, they're vulnerable to a technician programming them incorrectly. They have umpteen versions of software, firmware, and even controller types. What we can't simulate well are the actual controllers. So what we do at Typhoon is controller hardware in the loop testing. And I'll talk a little bit more about this. But what we're trying to emphasize here is that we can put the actual controllers in the loop together with a model of the power electronics in order to create that digital twin that's going to allow us to test to that fidelity that's required. And because we have the actual controllers, we also have a mechanism to test the controller software that's running, because it's running on the actual controllers that are in our test beds. So we are an integration tool that is extremely high fidelity, and I'm going to talk a little bit about interoperability. So just to kind of drive this point home one more time, I call this slide testing methodologies, but really what these cartoons represent is different ways to break apart that microgrid. So you can get all the pieces of the ship. You can have everybody deliver these, put it all together, and you can start testing that ship after you've put it all together. If you do that, you're accepting a whole lot of risk, both in terms of safety, because you're running everything up to full power with all the current and voltage. You do have the highest fidelity because it's the actual ship. But man, if you screw something up, you're looking at a $4 billion commissioning cost. So you could just go right into your design process, just order all the components and kind of cobble them all together. The other thing you can do, and this is where people kind of start disconnecting from this concept, is you can do an all simulation or all software based approach. And you know, there's a whole bunch of software suites, and electrical engineers, and I guess I'm a mechie aerospace guy, so you know, take this with a grain of salt. But there, of course, electrical engineering is a very, very broad umbrella and encompasses a whole lot of things. But there's this tendency in engineering to get very target focused on my problem. There are many like it. This is my problem. And then when I want to do something else, I throw it across the fence to the thermal guys or what have you. And in electrical engineering, you hear a lot of discourse back and forth between the power systems guys, the power electronics guys, what have you. They each have tool sets, and everybody wants this, you know, magic BB software suite that you can come and model everything. And the problem here is, number one, you've idealized the control, and there's all sorts of issues with that. This really doesn't have that high fidelity, and people are kind of surprised by that, but that's because typical laptop computers, PCs, they're not capable of doing deterministic calculations because of the way they're configured. So you really don't have the fidelity that's required. And yes, they are very low cost, but you can't, there's a huge amount of risk with this all software approach. So what the automobile and aircraft industries, and now power electronics and microgrid industries have done, is they've come up with a way to kind of have their cake and eat it too. And we talk about these three concepts at Typhoon of V-HIL, C-HIL, and P-HIL. What we mean by V-HIL is we're going to model everything to include the controllers. We're going to idealize the controllers. We're going to have models of the power electronics, it's not a complete oxymoron because we're still going to take this and we're going to compile this on an FPGA-based real-time emulator to get some of the fidelity up. And we're going to call that V-HIL. And this is going to be very useful in concept and kind of detailed design steps and project management, but it still does not get after the real issues of getting all these components to play nicely together. So what we're going to do at Typhoon is we're going to color up this cartoon. We're going to put actual controllers in the loop. And we really like this because these controllers are actually very hard to model. Or if you idealize it and you say, hey, there's no communications latency between the controllers and this one works exactly to spec every time. That of course is impossible. So we're going to put this impossible to model piece actually in our test bed. So the actual controllers, and then the model of the power electronics stages that we think we can do very accurately, and we can prove that. We'll model those, and we're going to build these C-HIL test beds, controller hardware in the loop test beds. And the result is we get very, very high fidelity. Cost is still in line, but this is approaching a digital twin of what we want to do. Now, we can do power hardware in the loop. And we view this as really something that component manufacturers need, because I keep on talking about the accuracy of the model. At some juncture, you have to build the inverter and you've got to run full power to it and make sure that it's going to behave as you've modeled it. And that validation process is absolutely critical. So you do need a P-HIL capability where you put an amp in the loop here and you're running that inverter to full power. But again, this is something that component manufacturers can do, because if this component manufacturer can run P-HIL, validate his model, then when he gives it to me as the system integrator, all I need to do is drop his controller together with his validated model, and I'm cooking with gas. I can run my system here. So these three components, V-HIL, C-HIL, and P-HIL, we think reduce the risk immeasurably and inform this process to get to this microgrid. So what does this look like on a typical project management curve? First of all, V-HIL, virtual hardware in the loop, really helps you with this feasibility studies, concepts of operation, can we make sure we've got the requirements right, even down to detailed design. But once you start moving into that software and hardware down select, we want to start building that C-HIL test bed. So you can do this pesky little thing called verification and validation of your design. And not just do it, we want to do it in a way that informs and goes back and forth in this design process. So if we've done all this work in V-HIL and we get a microgrid design, say it's a electric train locomotive, and then we get all the way over here and somebody goes out of business, or we have a different motor or a new battery or something that we just absolutely want to incorporate. We want to have a way to go backward in the process and update all this, frankly, steady state analysis so that we can incorporate it in our high fidelity dynamic analysis. So we're going to do that using this C-HIL test bed for validation and verification. Then we're going to use that C-HIL test bed to help us during commissioning of the actual microgrid, of that chip. So imagine engineers have a problem getting the gen sets synced up. They call back to the guys who have the C-HIL test bed. They replicate that problem and they find out, oh my gosh, you guys programmed the controller wrong, or yeah, there's some kind of issue. So that C-HIL test bed informs this commissioning process. we start talking about that C-HIL testbed as a multi-physics digital twin at this juncture. And that digital twin, and I won't belabor this point because there's a whole lot of things that we can talk about. And hopefully we'll have some questions and answers for them. But once we have that digital twin, we've got a very, very powerful tool to use over the life cycle of that system. Say it's that ship or a microgrid somewhere. If something gets damaged, we can replicate it. We can figure out how to fix it using our test bed. We can do repairs. We can do upgrades and replacements. And this is kind of a nod again to my naval background. You know, ships, they come out of the yards or they come out of commissioning. They operate 3 to 4 years. There's some changes and upgrades and overhauls that are done during that, but then they bring them back into the yard and do these extensive upgrades and repairs about every 4 years. And that's a brownfield requirement right now. I mean, if they change something, they've got to start the engineering exercise all over again. You can imagine if they had a digital twin to inform that process, this recommissioning after the yard would be much easier too. And that's why I've got these 4 bullets. The other thing that's very interesting is we're starting to get into cyber and artificial intelligence also with this technology. The cyber piece is if I've got a digital twin of my microgrid, then I can give that to the red team and they can attack it all day long and try to drop the grid or make something go wrong. Even a firmware update, when you think about it, is a kind of cyber attack, albeit one that you know exactly what you're doing when you're doing it. But if you've got any experience with microgrids, you know about this 4 of the bricked system, because you went in and did a controller update and it bricked the whole thing and it just doesn't work. And you've got to get a bunch of engineers out there to try to unscrew it. Well, why not test that firmware update against your digital twin to de-risk what you're going to do when you actually go to the field? The AI piece is equally interesting. If I can run a simulation with, say, a microsecond sample rate, and then I scale it and I have the same sample rate, but I'm going to run it faster than real time. I'm going to run it at 500 nanoseconds. I can actually finish the simulation with enough time that I can inform the ship's captain, hey, if you don't shut down that pump, or we just took a cruise missile in the side of the ship and lost some kind of cooling system or something. If you don't change what you're doing, I've run the simulation and the next thing we're going to lose is the radar is going to overheat or something like that. So you can start using it for AI. The other thing we can do is we can generate data sets from catastrophic events that can be used for machine learning. Because right now, yeah, we can all talk a mean game about that data and we're going to put our algorithms on it and have machine learning. But if you don't have a data set of that casualty, and how do you really generate a data set for a casualty if you don't have a way to simulate some kind of catastrophic event? A C-HIL testbed can help you with that. So we're really excited about that impact of our technology in the future. So how does Typhoon do it? One, we're vertically integrated. And what that means is we do our own hardware. So you see this real-time emulator, something we call a HIL 604. That's an FPGA-based device using Xilinx FPGAs. It's got 2 to, in our newer devices, 3 ARM cores to do signal processing, that is model the controllers for that V-HIL piece, and then FPGA cores to model actual power electronics. So we do that hardware. We can do controller interfaces so that we can put together this test bed of a system. We do our own software also, and the reason why we do that is in order to get that fidelity, And there are two ways you could do this, and our complementary capabilities. You notice I said complementary, not competitive, because in my mind they're complementary. They're doing different things. But SpeedGoat and Opal RT are also hardware in the loop capable solutions. They run MATLAB Simulink. That's great to leverage the awesome capability of MATLAB Simulink. The problem in this very, very high fidelity realm is when stuff doesn't work quite right, do you call the software guy or do you call the hardware guy? And more importantly, do they talk to each other? You know, do you walk up to a computer that says, under no circumstances are you to upgrade from LabVIEW 2014 because we got everything working, and don't update. At Typhoon, we decided to have an integrated solution so you've got one call to make for troubleshooting, and also so that we could guarantee any model made today will be forward compatible with our solution tomorrow, which is very, very important. So we wanted both our own hardware and software, and then we provide services too, because this stuff is complicated and we need to be able to help our customers do that. So how we do it is first as a vertically integrated solution. Then we offer a number of approaches for the real-time emulation capability, everything from component development tools like our 4 series. And when I say component development, you'll notice they don't have as many cores. They still go very, very fast. The sample rate is common, but they may not have as much input output, and you may not be able to stack them to scale as much. So we have our 4 series, and then we have our 6 series. And these are our powerhouses really for system integrators, because you can take these 604 and 606, stack up to 16 of them. So you start doing your math for Marines here, and if we can do 8 3-phase detailed computer converter models in one 606, if we can do 16 of them, now we're up to 128. We're starting to talk about being able to do an entire ship set. And then you see the fidelity, okay. Then you see the I/O, and the I/O is important because that's how many controllers we can interface. So you have to model the power electronics, and then you have to be able to interface the controllers. So you have those two bookends in our parlance for your C-HIL testbed, and we maximize both of those in our 6 series machines. The other component of this, because again, we're digitally controlled, is digital communications. And you see all the different ways we can communicate, and you can see which are our 4th generation or latest machines. The HIL 606 just came out this summer. HIL 404 just came out last year. But what's the biggest difference? These guys are using fiber optics, this SFP port. So we can talk fiber, we can really maximize that capability of that FPGA chipset. And then you're starting to see EtherCAT, which is, if you do any research on it, big problem with Ethernet is you can't do deterministic communications with it. Biggest difference between EtherCAT and Ethernet is this capability of doing deterministic. That is, we know exactly what time these things are going to arrive, these packets of information. That also is where this time synchronization piece becomes so important in the HIL 604 and 606, is time, communications, time, input, output, modeling capacity, time resolution. That's why you see all of these on this slide. Just kind of highlighting all those things. You'll notice, we're getting into the 200 nanosecond realm. One thing that's interesting in terms of Typhoon's architecture, when you stack our devices, so say you put 2 to 16 HIL 606s, you lose one time step. And what that means is you can run a stacked set of 16 devices at 400 nanoseconds. versus 200 nanoseconds. That's really interesting because that's not true of some of our complementary capabilities. They can run very fast for certain capability sets. So like say one inverter, they can test one inverter. And they do some things, let's say, better than Typhoon. They can do thousands and thousands of nodes for, say, transmission models that we're not really configured to work with. But if you want to put together a power electronic system with more than one inverter and associated digitally controlled protection and whatnot, we can put together a ginormous solution and still run it at 400 nanoseconds, which is critically important because of that time, as I've already described. The other thing that Typhoon does, and I'm running up, I want to give at least 15 minutes in case anybody's still with us that wants to ask questions. You remember that Lego block and this panacea that microgrid people want to be able to turn microgrids into building blocks, and they just aren't. Unless you buy like Caterpillar solution, which has energy storage, inverters, genset, and it plays pretty well together, right up until you have to integrate it with an existing genset or get it to play nice with the grid in that area. This Lego block approach just escapes folks. So what we do at Typhoon to approach that is we have something we call HIL compatible. What that means is we have a controller interface and a model of that system. So you see here our friends at EPC Power in Southern California, they make inverters. We've got two of their actual controllers in this box, and this box does all the signal conditioning that those two controllers need to be tricked into thinking that the model they're controlling is an actual inverter. And that signal conditioning, just think of it this way, is this is the front of our real-time emulator. Its I/O is plus or minus 10 volts, digital or analog I/O. Well, if this inverter or that relay needs a 200 volt signal, that's the signal conditioning we're talking about. And we can do that piece as an interface for that, what we call HIL Connect. We can model it, we have the controllers, and then what we can do, and this isn't an all-inclusive list, we can start building these test beds in a Lego block approach. So you see here a whole bunch of distribution that we've got, Schweitzer, various types of Schweitzer relays, tap changers, etc. This is basically grid modernization here. You see microgrid controllers that we've done, genset controllers that we've done, wind turbines that we've done, and finally inverters, which typically in a microgrid tend to be the most important controller because they're what? They're the fastest. They have to operate at the fastest rate of speed or frequency. So I talked a lot about this, and I don't have the time to demonstrate this effectively, but I mentioned those lines of code and how do you get after that? How do you test that? And essentially what you have to have is a way to automate that testing. You want something where you're going to run a real-time test of your system and you need every permutation of that drive and that controller covered. And it's just exhaustive, meticulous work. Well, you may have caught it that Typhoon is Python based. Python has an awesome test scripting capability they call PyTest. Typhoon has just built on that with an API that makes it easier for a non-Python user to use it. And we've developed this Typhoon test approach where you can take that system, that microgrid that you've got in your C-HIL test stand, start it running the test. So it's going to go through every permutation all night long. And when you come in the next morning, it gives you this Allure test report. It says how many tests it ran, how many were passed, how many were faults, how many were actual failures, and it can do all of that for you. So very, very important capability here. I started with why, with that picture of the ship. and the problems the Navy's been having with it. That ship is still not fully commissioned today. It's been sailing around for 9 years. So I'm going to end with why too. We want to meet requirements, and you see this is starting to become very, very important in the microgrid, UL 1741, IEEE, BDU, which is European, etc. We want to reduce risk. We think a model-based approach is absolutely imperative when you're talking high power electrical, power electronic devices. Both in terms of personnel, we don't want to turn anybody into a big blue spark any more than we want to turn equipment into a big blue spark. So if we can do that in a model-based environment, we're going to reduce risk. We're going to make sure it works before we build the actual thing. That in turn reduces costs. Nothing else. People understand commissioning takes forever. If we can cut commissioning time in half, it's a win. And then we want to enable lifecycle systems engineering. We want to improve that support over the life of the device. We want to have a way to implement resilience and things like that. So that's why we do it. We try for a lot of interoperability, and you see here, I said multi-physics, but I spent too much time on it, but you see we can bring in JMAG, finite element analysis, motor design, electromagnetic capability of this software suite. We can bring it into our model-based solution. FMI, FMU is the direction I think that model-based systems engineering is going, and we can bring that in along with C functions and things like that. We're talking PSIM, ZEISS, even MATLAB, Simulink. We don't have a magic BB that allows you to pull those models in, but we have a way to pull them in. And if nothing else, we can color up that model as Typhoon if you want us to. But OpenDSS for load flow analysis and power system simulation, OpenDSS can now be brought into Typhoon. We're constantly working on this interoperability of software and communications. So, got my slides out of order. This is a paid political announcement in the sense that we are having a webinar tomorrow, if you're interested on power systems protection testing. And what's so fascinating about this is this guy, Justin Smith, who's going to be doing most of the talking, is going to be talking about real world application of hardware in the loop, finding problems with microgrids before they manifest in the field. But the reason why I say I'm out of order, I just wanted to show you a couple pictures and then we'll open it up for questions. This is a grid modernization test bed at Duke Energy in Mount Holly. And look at all these controllers that they've got in the loop that they can run various tests with. And this is that energy storage system, that inverter. You see they're doing it with C-HIL 604s. And this HIL Connect, that's the signal conditioning that allows you to pull those controllers in. This is an interesting one. This is a commercial marine power system. What I find as a guy who spends a lot of time trying to figure out how to help the Navy, as the Navy's starting to become more and more electrified, we get this big argument back and forth. Should we have an AC bus or a DC bus? And I don't know if it's true that Thomas Edison and Nikola Tesla didn't get along, but I absolutely know their technology doesn't get along because of that conversion requirement between AC and DC. What's fascinating here is ABB said, okay, well, I'll tell you what, we're going to test both distributions basically on the same thing. We're going to have 4 diesel gensets, 4 active rectifiers, 2 propulsion units. These are Azipod electric propulsion for their ship. And we're going to put all this stuff in the loop, and then we're going to tell the model, you're a DC bus, and we're going to run all of our tests. And then we're going to tell the model, you're an AC bus. We're going to run all the tests. Imagine how much money that saved them being able to test this exhaustively in a model-based system solution versus building 2 different ships and knocking their head against the wall. This is Remontoa Shipyard in Poland, where we've got a test bed that they've got. Active rectifier controls, the Schneider Electric. Start seeing some interesting utilizations here. Filtering is a big thing aboard ship that they need to do. This is MIT Lincoln Labs. This is microgrid control and their test beds that we help them develop, and we've got ongoing research that we do, or not that we do, that we enable at MIT Lincoln Labs for testbed, or excuse me, for microgrid. This is kind of an interesting one because IHI is right there in Chicago. Energy storage is what IHI is all about. We help them model their energy storage requirements. Here's another microgrid, interesting, just showing the different controllers. There's the distribution. You see the Schneider Schweitzer 751 in the upper left here. There's the wind turbine controller on the right. Here's the genset, and here's the solar. This one happens to be missing energy storage, but it's still a microgrid. Big, huge battery in Southern California. Some of you might remember 4 or 5 years ago when they had that gas leak and they had to shut down those peaker plants. They replaced them with a giant battery that we helped with. And I'll wrap up here by saying, hey, I hope you guys will come to our website. We've got online training, and would love to talk more with you.